Morning, everyone. Good morning.
Morning.
So, put this down. Well, I hope I don't disappoint you after all what Anthony had said, but I'm really honored to be here and just tell you a little bit about the work that we are doing in Chattanooga. And I want to mention that a lot of it is ongoing research, so I'm going to show you some of the work it's going on and some of the results that we are seeing there. As Anthony mentioned, there are at CUIP and UTC, we are working on several areas. Transportation is one of them. I'm going to be mostly focusing on that. Depending on how much time we have, I might talk a little bit about other topics. That's what I put smart mobility through connected infrastructure as the title today. You all know Chattanooga. I moved to Chattanooga 16 years ago when I graduated from Georgia Tech. I always say I moved up 100 miles from Atlanta to Chattanooga. I wasn't sure if I was going to stay or not, but I've been there for 16 years and loving it. It's the kind of work that we are doing in Chattanooga, the collaborating environment that the city has is really, I know you all know about Chattanooga, but we go many different places. This is unheard of because a lot of times we would get this question of, who do you go talk to your city? You know, we have Mayor Kelly here. We work very close with the city, with other municipalities in the city, and I want to talk a little bit about that. And the work that I'm presenting is really a result of a work of a huge, big group that is working on it. It's not just UTC. There are a lot of collaboration going on. You all know Chattanooga has been known as Gig City, and it has been a city that had, it's over 10 plus years ago, the fiber was deployed. That provided the infrastructure for a lot of work that currently we're working on. So it has been built on that infrastructure. And one of the visions that we have is Chattanooga become the test bed, the city scale test bed for the future of mobility, in terms of both connectivity, in terms of automation, in terms of EVs. Late last week, it was announced that City of Chattanooga, UTC, and some other partners have received a total of $9.2 million. Half of it comes from federal, half of it comes from our industry partners, to build a test bed for the EV charging stations as well. So this goes beyond the connectivity and automation. And what do I mean by the connectivity there is, you know, a lot of vehicles are coming up with a lot of sensors on them. They have already come with the sensors. We see the vehicles that are doing adaptive cruise control. They can do the lane adjustment. There are automated vehicles on the road now, but they're all counting on what is built on the car. So OEMs are working on that. What we are doing is beyond that, in terms of we're not touching anything on the car, but being able to let the cars talk to each other. If I'm driving down the road, there was a black ice on the road, let my car know the cars around me that there is something that they have to be cautious about. If the infrastructure has seen an obstacle, that can be broadcasted and the cars can decide based on what other information that they can see, make that decision to make the streets smarter, make it more efficient. So that is what we are working on in terms of the connectivity and in terms of making it a connected infrastructure for vehicles. And I mentioned this, I wanted to bring it as one of our first few slides, that this is a collaboration that we have at Chattanooga Smart Community Collaborative. This about 4 plus years ago, a group from the city, county, EPB, CoLab is our entrepreneurship entity there in Chattanooga, and Erlanger Hospital is our public hospital, UTC and the Enterprise Center, we all came together. This was born, and this is a result of we are meeting every month. Representatives from all entities come together, and this has provided a lot of opportunities because we all work in our silos. You know, me and my colleagues know what's going on at UTC, but we don't necessarily know what is going on at EPB or the city or the county or the hospital. So this is providing us this opportunity to talk to each other for projects that need a collaboration, needs multidisciplinary really approach. So we talk about the projects, but it doesn't end there. If there is a solution, that's always a thing that we go back and see that, can this solution really be deployed? Can this be applied? Because a lot of times, we researchers might think very theoretical. Something that I can do it in my lab, on my computer, but can this be applied and will have an impact or not? So this has been a great venture for us, that being able to have this entity to come together and collaborate. So a little bit about CUIP. CUIP was actually established around the same time that the collaborative was established. And the goal here is we don't do research for the sake of research. That has been our main goal. We do quite a bit of citizen engagement. So a lot of times before, actually when the CUIP was at the very beginning of our activities, we started working with both Enterprise Center, and we have a urban sociologist faculty at UTC, Chandra Ward, and she and her students, they come together and they did a lot of focus groups, a lot of meetings to understand what the different levels, what do people see as challenges. They talk with the city, they talk with the different municipalities, with citizens and such. So we want to make sure that the research we are working on is really will have the impact. It is a really, I want to also give credit to the students at UTC. This is a great opportunity for our students because they are working on real world problems. And this is undergraduate, graduate students, and now we even do capstone projects with high schools. So this is really providing opportunities for students to be really involved in that work. And this is supported by the University of Tennessee system, and obviously we are, it's there because of the infrastructure and innovative culture that Chattanooga has. These are the areas that I have: the mobility, health, energy. These three are more advanced. Like in our group, we work more on those, but there are some activities in terms of water and other areas as well. So I did already talk about this, but again, I just wanted to have a list of the universities. This is a lot of, a big team, a lot of universities, city, municipalities, and we also have some international partners that we work with them on these, and we have national labs and such, and industry partners. Okay, so when we started talking about smart cities, a lot of times we get that question of what is our goal? We wanted to have some metrics. So these metrics has been defined over the past few years, they evolve, but these are the sets of the goals that we have, and this is what we are working towards. And I will be talking about some of these, but it is like Vision Zero. I know some of the other cities here have that goal of making the traffic fatalities to zero. So our goal is to go going for that. And fuel consumptions, faster commute time, emissions, community participations, and also emergency response time. So there's a lot of these things that are, again, I'm not saying we're there, but we are working toward that. These are our metrics that we are measuring our performance against. So this shows a little bit about, if you want to understand about fatalities or about the accidents. So our main goal is to understand what is today going on there. So these are there are 3 different test beds, and soon, as I mentioned, the DOT grant that was awarded, was announced last week, is going to increase this geography of the test beds. But this is something that we have been working on. The green area, the green marks are, this is along MLK Smart Corridor. This was established 3 years ago. And this is 11 signalized. In fact, actually, as of 2 weeks ago, we added to the other side of 27 as well. But I'm going to talk about it. But we wanted to, the beginning part of it is more downtown businesses, and as we leave toward the east, it becomes more residential. We wanted to understand how people are using the streets, where is the safety of the streets and such. So that is where the green one has been live. We are collecting data 24/7. I'm going to show you some of those results. Last October, we received funding from National Science Foundation to expand that test bed to the highway. And this is because a lot of work that we have so far been working on is related to pedestrian, cyclists, and such, but going to highway now would allow us to be doing more work related to automation and connectivity in a faster speed. For example, platooning, lane changing, merging, and such, that we won't be able to do it in the urban environment. And one of the things was, when we were working on MLK, these are city poles. This is city-owned poles. So things were going much faster. But things changed with TDOT as well. Now they are great support. They are working with us. We have regular meetings with them. We thought it's going to take much longer, but by this October, we are still on schedule to have those 9 poles along Highway 27 as well. Now we're working with the state, and these are all the things that, me coming from a research background, don't know that, because we were always like, okay, it's going to be a sensor, an IoT device on a pole, but it's very different. Now we are dealing with it's a state-owned poles, but these are the things that we are learning through these processes. And also, we are going to be early next year, we're going to be expanding it to the red pole, like that area. It's going to be 27 additional And this is going to be, again, it's going to be a larger part of downtown. The other good thing about it would be parallel streets. The UTC sits here, so there's going to be more even walking and pedestrian and crossing and those happening there. And also it would go to some underserved communities. And there are some other pilot studies going on there in terms of public health, in terms of transit and such. So we will be able to bring different pilot studies together and work with other partners in that area as well. So what do we mean by testbed? Each of the poles currently on MLK are equipped with different IoT devices, different sensors. We have different computing capabilities and different wireless communication capabilities. So just going through those a little bit, we have cameras, we have LiDARs, some of them have radars, and then we have air quality and microphones on those poles. One of the questions we get is when we have cameras and audio, are we watching people, are we listening to people? And the answer to both of this is no. And that is what we did for 6 months at the beginning. That's what, when I was telling you when Chandra was doing her community engagement, that was one of our projects that she was working on, to listen to everybody and understanding the challenges. So what we do is we have edge computers on the poles at each intersection, and also being Chattanooga, all the poles are connected to the fiber, so data directly is transmitted to our data center. Everything is processed in real time and dropped. So we don't store any videos. We don't need to know Mina across the street. I just need to know a person across the street. That's all we need to know about that. And that is what we are storing. I'm going to show you some of the examples of that. And then in terms of computing, as I mentioned, we do, so those of you that do computing, and those, like we do some at the pole in real time right there. And the cabinet, the traffic cabinets next there, next to the traffic controllers, we have edge computers there. And then order through the fiber goes back to UTC being processed at the data center locally, or we send it to Amazon, so some of them is being processed, some of the data that it needs more power, we send it to AWS and is being processed there. And in terms of communication, wireless communication, again, some of you might remember that FCC had allocated a specific bandwidth for vehicles first, but what happened was at some point things changed. So all the vehicles were supposed to be with DSRC, dedicated short-range communication, but things changed. So we originally put DSRC on all our poles, but we removed them, and now we have dual units. The standards is not established, so we don't know how the vehicles are going to communicate with each other yet. But we want to make sure we have a test bed that can accommodate either one of these technologies. So that's what we have, dual unit. And one of the goals about this test bed is we don't want it to become obsolete. So really, we keep making it evolve, adding more technologies and updating it as needed. And we are collecting over about almost, and at this point, almost 1 billion data points daily on these 11. So it's really a lot of data that we are collecting. But we also have built this dashboard, and I'll see it, depending on the internet, I might be able to show you in real time the dashboard. But the dashboard shows different metrics. We look at each intersection, how many cars are crossing, how many cars are, and within that, maybe I shouldn't say car, vehicles. Within that vehicles, what's the category of them? Trucks, buses, bikes, and such. And then we look at the different PMs, so for air quality, the particulate matters. We look at different PMs. There was one day, it was about like maybe 2.5 years ago or so, there was a building, sets of condos was building there, and we didn't know when things were happening, but all of a sudden we saw a spike in PMs. And I thought that the sensor was broken. So we went and we checked that, no, there was a building. So there are things like this. When you start collecting data at that level, there are noises like that in the data. That would be our job to make sure that we are not thinking of, oh, now all of a sudden the city has a bad air quality. That was not that. That was just really because the sensors was next to the building that was being built. So there are also those things that we do it now in an automated way, that we clean the data before storing the data. And other metrics that you see here, for example, this shows arrivals by phases, by the traffic controllers, how many cars arrived by green or when it was green light or when it was red light, because we want to make sure that the cars are not being stopped at the red light all the time. The number of near misses, I'll talk about that in a second, and the average time for pedestrian. We want to make sure that we're not giving priority to the vehicles only. At least we want to understand what's going on the streets to be able to then we see that what interventions needs to happen. And we also received traffic data, traffic controllers data from all the traffic controllers, where basically we know all the phases, the time of the phases and such. So this is a good sets of data to be collecting. So when I was telling you about the simple visualization that we are doing is, so each object is getting a label. It's just having an ID number. And is it a car? Is it a person? And that's it. So that is being the location of that and also the time of that. So that is being stored for us. And then afterwards, we can go back and build on that. We can build a digital twin of what was going on at that time, completely in a digital format. But again, it would be just an anonymized, like it's just a person. That's all we know. And we have been building some heat maps. This is actually one of the first projects that we did. So this is about 3 years ago. We wanted, one of the very first project was pedestrian safety. So this is just mapping where are the pedestrian. You can see that pink is the pedestrian. And there are some pinks here, which because there's a car, and the cars have been removed. There are actually usually cars parked here. This is 2-hour free parking and campus is to your right. So you can see that's a lot of parking happening in that street. So these are the things that we have been collecting data and visualizing it to understand where are people crossing at undesignated areas, or how buses are driving. Are they getting too close to the bike lane? How safe our bike lanes is? How much our bike lanes are being used? So all of these are the type of data that we can collect. So what have we been doing with the testbed? I talked about, we do quite a bit of real-time data processing, and I'm going to go through some of it with you. So when this truck comes to the intersection, from the time the camera sees it till the time it leaves the camera view, we want to be detected as one object, because we are counting the number of vehicles. We are counting, we want to understand the time, the wait time and everything. So we want to make sure that we take that object and have it the same car versus keep changing the label for that. The other thing is, we don't know what's happening in mid-intersections because we don't have cameras everywhere. But we want to understand what was the travel time between them. And we don't do any license plate readers or anything like that. We don't collect any identifiable information. But I would like to re-identify this vehicle. So if this vehicle was at the intersection of MLK and Lindsay, and later on I see it at MLK and Houston, I want to have the same label. So we do that through purely computer vision. So it's just the computer, we have came up with an algorithm, we're still working on it, but it's basically, it detects the object, it gets enough features about that, and we can re-identify it later on. It doesn't have to be exactly in the same, in next intersection, it can be other parts when it goes to another camera view. It doesn't only look at the camera's data, but it also look at the time and the place. If you see if you think that is another car in the 10 seconds a mile away, that can't be the same car. So we also use that type of information to re-identify it. This allows us to be able to know the travel time of the vehicle in real time. And then we also collect data from our vehicle. We have one car that we collect. We drive the car quite a bit back and forth on the corridor. We collect the data. We want to understand, for example, trees, different season, how are those impacting the data collection, the data that can be collected from the vehicles. We even rented a van and drive those two together to see that how would that impact. If a van is in front of me, can I still get the data? Because if we want to build more safer and efficient, we need to understand what are the limits of it. How are we going to be able to understand, what are the things that can possibly block that data that is sent to the vehicle? So we want to understand that as well. And then also we have a project with Cardo, our transit, that also we collect their real-time data from them. How much gas, how much energy is being used, how many people are on it, when did they get on, off. Through that project, they collect the data. We are also having access to that data. So we built a digital twin, and this is what I mean by digital twin. So this is MLK, this is Georgia, and the number of vehicles, the timing of this all comes from the testbed. And my office actually faces MLK. So when I look at the window and when I look at this, that's the goal, is to see the same, and we do see the same. Colors are arbitrary, we just added it. But we do classification. We do say if it's a sedan or if it's a truck or if it's a bus. So those type of classification is true. So when we built this digital twin, now we can come back, and I'm going to show you an example of that, change the traffic timing, And then we can see the impact of it. Because this is a case that we have all the data from the actually what was going on that day on the street. So how many cars were there, and how many turn right, how many turn left, and then we rebuilt the scenario for different cases. How long were the pedestrian waiting? If we change that, how is that going to be impacting traffic and such? So our goal is really to build the digital twin very accurately. Some of our data comes at 10 samples a second, at 10 hertz. So we're collecting all of that. And whatever data, the more accurate, the more precision data we get, the better would be the digital twin. And this is our goal, is to be able to build this digital twin for a larger part, that we will be able to build some of these. I'm not going to go through this, but if there is anyone in the audience, I will be happy to talk to you afterwards. This is, again, something that the OEMs are working on in terms of what technology, what standard should be used. So we are working on these technologies, the GSRC and CV2X, but I'll be happy to talk to you afterwards. So some examples of what are we seeing, or what have we. So again, you see up there, it says time to collision. Time to collision is, if it happens, there's a record of it through 911 calls, or through that, we have access to that data. But if one of the very, and you saw one of our metrics was Vision Zero, to reduce the fatalities. To get to that, we also need to understand what are the intersections that have higher risk of accidents. And it might not have happened, but there are areas that the vehicle and it gets too close to a pedestrian, or a vehicle gets close to a cyclist. Those are the ones that we want to understand, and being able to pinpoint, and not just saying that Mina has seen cars are getting too close to pedestrian. What is the number actually? So being able to address that objectively. So this is again, Georgia and MLK. What you see here is we are identifying objects as a person or a vehicle. We are doing, what you see behind the vehicle is their trajectory. What was the path that they have came? The line in front of them, we are predicting where is this object going to be in the next second. If the future trajectories are going to be colliding, that's where it's going to be a red flag, that these two objects are getting too close and it needs to be addressed. And one of the questions that we usually get, which is a very right question, is not every car is going to be connected. Not every person is connected. How are we going to make sure that if we want to have some technology like this, it would be inclusive? And that is a project that we are actually currently having with TDOT, to understand that what would be the best way in terms of reliably and also with low latency to communicate this back to a person that is driving a car that might be 20 years old, might be 5 years old, and doesn't have the connectivity. How are we going to be collecting that? So there are several options, and I will be again happy to talk to you afterwards, that we are currently proposing and we are testing those. But this is the type of work that we're seeing, that we have seen these things and we are marking them. We have a number of each intersection, and we're seeing the ones that, like usually the left turn, it would get too close to the vulnerable road users, cyclists, bicycles. We don't have scooters, or not that many of them in Chattanooga, but those as well, that those are the ones that we want to make sure that they're safe, and where are the areas that there might be a risk for them. So when we are talking about being able to measure the distance, accuracy is very important. Our cameras are 2D regular cameras, so measuring the distance between two objects, with the camera you map them. It is 3D, but when you map them to one plane, then it becomes 2D, and it's hard to measure the exact distance between them. That's when we added LiDARs. The other good thing about LiDARs is we're not storing any camera data, so we can go back and check. But with LiDAR, there is no, so I want you to see this. This is a view of a LiDAR. It's the same intersection, and this is us collecting data. That's what I have. Our team also go out there and collect data. We just keep walking around and doing like different scenarios to understand what's going on. So what you see here is the pedestrian are green, and you can see exactly the path that they have taken. And the vehicles, any type of vehicles is red, and based on the size of it, we can understand that was it a car or was it a truck or a bus and such. And then this will be enabling us to measure the distance very accurately. And I want you to look at this case here, right there. And here the video of that. So this is the person that is crossing. And this was a case of near miss. It was not intentional. It was not intentional, but this is a case that it was a near miss. And these are the things that now we understand, and we are actually working on these to understand the left turns, how are they going to be impacting the safety. The other thing, there is a nonprofit entity in Chattanooga called Signal Centers. They work with those with disabilities. We try to reach out and engage with our community as much as we can. We had meetings with them, and one of the things that came up was those with wheelchairs. How accessible our streets are for those that are on wheelchairs. I mean, one of the things that they mentioned was the trash days. That there are days that a lot of times are, the people think that the sidewalks are blocked, and things that crossing the street, if you're a wheelchair, if you have a wheelchair, or if you're a parent pushing a stroller, or it's an elderly that needs a longer time to cross. What this technology is enabling us is, again, I want you to look at this. So, let me go back just a little bit. So, pedestrian is being green. And wheelchair, bus, anything with wheels, at this point, our algorithm is not sophisticated enough to distinguish between wheelchair and, we just need more data and we're collecting it. It doesn't distinguish between wheelchair and bike. However, we would be able to go back and identify it better based on the speed. And if it's a bike, it goes faster than a wheelchair. And we're not making any assumptions yet, but that's what there is. You just see one color. It's the yellow. So what we are doing here is we are identifying that there is a person on a wheelchair or such on the crosswalk. We know how long it's going to take them to cross the street because we can measure the speed. We have seen the object and we are measuring the speed. We also have the SPAT data. SPAT data is a signal phasing from the traffic controller. So we know exactly how long it's a green time for the pedestrian to cross. What if in real time we adjust that crossing time by a second or two to make sure that that person is crossing the street safely? And that was something actually we had an international data challenge January of this year. And the teams that won was from University of Michigan and a university in Korea as well. So it was really, we had but one thing I want to say, I made it sound very simple, adding 1 or 2 seconds. But you all know that adding 1 or 2 seconds in one intersection can completely mess up the network. So the goal is how can we do that in a more global, not necessarily the whole city, but not just focus on one intersection. Think about a little bit of a couple of upstream and downstream and do not just focus on that. Again, as I mentioned, these are all research projects, but I'm going to show you some of the outcomes of this as well. That these were the thought process going through some of these projects, and I'm going to show you some of the impact of them. This is not Chattanooga, but I'm going to show you something about Chattanooga as well. So one of the other things was wrong way detection. I didn't know, I come from computer science background, so I'm not a transportation person, but I work with a lot of people from transportation. They were telling us about how many times cars go wrong direction, especially to highway. So we are using this technology for that as well, but before having any of our sensors up, we worked on data that was available from other places. And you can see that using LiDAR data, you can understand what is the regular trajectory of that area, and then detect things like this. When a vehicle starts from here and end there, which is not a right way to go, or do a U-turn in the middle where they're not supposed to do. So these are, again, things that we are collecting to understand the places that it's a wrong way detection, wrong way traffic flow. But this is what happened in Chattanooga, and this is Highway 27. This is the off-ramp. This is a one-way street, but you see that vehicle is going the wrong way. And if they realized that we had the trajectory afterward, they turned around. But these are the things that, how are we understanding these are going on? Where are the areas that these things are going on and being able to address them? So I think this is common to all of us. You have been sitting in a red light and you're thinking of, why am I waiting here when there's no car in the other direction? I mean, I think it's a common thing, and some cities like Chattanooga has the actuated version. And actuated is basically, it looks at the traffic that's at that intersection and adjusts the traffic phasing based on that. So we have looked at one day, we used one day in May as our example. And this was what's going on at the Houston and MLK under actuated. You see all the vehicles that are arriving in red. And that's something we don't want to have. We want to make sure that the vehicles get to the intersection at the right time, at the green time. And I'm going to get to this in a second, but I'm going to show you the result, and then I'm going to tell you how we achieved it. So we applied it with a reinforcement learning. I'm not going to go through the details of the algorithm, but it's just basically an artificial intelligence-based algorithm. That we applied that, and you see that how many more vehicles are arriving at the green time and are passing through the intersection in the green time. So how is it working? We collect data from, I told you about all these data sources that we have been collecting data. We have our data collection and such, but what's going on here, this is how we are doing the optimization. We're doing two things. One is we are looking at each intersection independently. At a localized intersection, we are looking at what is going to happen in this intersection in the next cycle. And that's the main difference between what we are doing and the actuated. We're not looking at what is going on now, because the traffic comes from upstream or downstream. It has to come from either way. So we can, with a high accuracy, know what is going to be the traffic in the next phase, and plan the phase based on that. And that is, we are looking at it from localized, but we all know that traffic controllers do not work at local level. It is a huge thing about global, because they are coordinated, and that's the important thing, how much should be the offset values and such, and that is what's going on. So after we applied that, and these are all still in simulation, and I'll show you that. We saw that Pine to Central, Pine was beginning of our test bed at the Highway 27, and it goes east through Central. We saw that the time travel was reduced by 20% through this optimization. And then the other thing about it is that EcoPI, I'm not going to go through the details, but energy savings from that was about 15%. But one thing I want you to pay attention to is this yellow box here. And that is our goal of, we don't want just the cars to pass through fast. What about the pedestrian? Are we telling them to stay there for 5-10 minutes because we are saving energy and we are just reducing the emission? That cannot be the case either, because in middle of our perfect optimization and somebody wants to cross. That's the real world. In my optimization, I can just ignore that yellow box and I say that world is good, I have solved the problem, but that's not the case, and we all know that that's not the case. So, or we have an emergency vehicle that needs a priority. We have it in Chattanooga also. There is a project related to transit priority, allowing the bus to get the right time to, we don't want the bus to get to the station earlier, but we want them to get there on time. So how can we adjust that? So all of those things are going to be changing this optimization, and that was one of our challenges, to make sure that this can be done in real time. It can adapt. It cannot be something that I optimize it once and I let it be that way. It has to be adaptive, and that's what this system is called. It's an adaptive traffic controller. And this is, you can see a simulation of that. Like everything else, when we do it in our computers, we can run any different scenarios. So this is what we are doing. We have been working on this for now. This is actually a DOE-funded project. Our partners are Georgia Tech, University of Pittsburgh, and both of these universities are very well known for the traffic engineers. And we work also with Oak Ridge National Lab as well on this. So the goal is on the third year, which starts next year, we are going to be implementing this on the street. But before that, we are going to be ensuring the safety. There is a backup plan that it always would go to that, and then making sure that it has run all different scenarios. Everything that goes wrong, it can be run on that. And that's the beauty of digital twin that provides us that opportunity. So the one on the left is a reinforcement learning. The one on the right is the actuated. You see the same traffic is coming. This is the data from that day we are collecting. But you see that in the case of the reinforcement learning, the queue is shorter. We are allowing more vehicles to pass through faster and adjust it. And we currently don't have the pedestrian modeled in our model, but we have the constraints of pedestrian safety in the model. So we do have the minimum time. And you can see that, examples that queue is building up. And again, this comes from the data from that day, and the other one would allow the vehicles to pass through faster. Changing gear a little bit, because so when we talk about the testbed, we know, we are collecting our own data, basically. We have put the devices out there and we have been collecting. But there are other sources of data that every city has access to, such as 911 data, like all the accidents records and such. And these are the numbers that has been happening in our state and our county. The number of accidents, the number of traffic deaths, and the number of, we have been working with the Hamilton County 911 with to understand, we want to understand where are the areas in the city that have higher risk of accident, and potentially know that why is it happening. So what this one is doing, again, I'm not going to go through the details of it, I'll be happy to afterwards, but we get the data from 911, it's an open source data. We work with the TDOT, we get something called E-trims, which basically is road geometry. How many lanes, does it have shoulder or not, crosswalks or not, the curvatures, we get all that information. ArcGIS gives us a lot of access to the GIS data from all the streets. And then we get data from dark sky now. We want to understand the weather data. We have built our model. I don't go through all of that, but these are the models are building. We want to know where predicting the model. So where are the accidents going to happen? And then potentially, what can we do to avoid that? These were the numbers. This is just purely visualization. There's no optimization, no model, prediction, or anything happening. But this is just, we wanted to understand, when we get all that 911 data, we graphed it based on different days. You see that these are different days of the week. Weekends, the number of accidents goes down, and you see that the peak number of accidents for the weekday is 5 p.m. for every day. Fridays is at 4. And then you see that like Sunday and Saturdays are different as well. So there's clearly a correlation, so that we can understand something from this. The other thing we did was, we built spatially, how does it look? So what this one is showing is where are the accidents happening at the different time of the day, how this accidents is moving through our city. And from this morning is where is the higher number of accidents in the morning in different times. So again, spatially is also correlated. What this enabled us was to look into, there are areas that there are more accidents. This is, those of you that are familiar with Chattanooga, this is North Chattanooga. What we saw was in that hex, there were 80 plus accidents. It's, and over time, we received the data from the time that the data was available. Clearly, this is an area that speed limit, I believe, is 25 or 35.
35.
35. Thanks, Mayor. Yes. So, and
Under truck. Is it okay?
And but so this was something that we our team saw it. This is an area that needs some attention. But we are not, again, traffic engineers. So we went to the city and we talked with Kevin Comstock that used to be with the city, and we asked him, what is going on here? And they realized that there was this pole was too close to the road. This is a part of city, everything is so tight. So there wasn't much room to move it. It was moved by very slightly amount, and some of this reflective signs was added. There has been no accident there since June of 2019. So, I mean, things like this are really, it's just data provided us because we were looking into it, and that's why you see all these dark colors here, that why is it that this area was. And again, we don't have, this is not part of our test bed, but there are technologies that is mobile sensors that you can put somewhere and understand what's going on there, to be able to put it somewhere that it was red flag and collect the data over 2-3 weeks and then go back and see what's going on. And then we have built a model now that predict where are the areas, depending on the time of the day, depending on the day of the week, that are more prone to accidents. And then we go back and continuously, like what you see here is the data on January 23rd, where we predict where the accident is going to happen. But we looked at the data up to that day, up to January 22nd. We built our model, and then we are looking at, okay, so this is where we predicted the accidents would happen. What was the probability of it? What was the severity of it? The algorithms are not perfect. There's a lot of false positives. But the goal for us is to not have many false negatives. If the accident was going to happen, that's our goal, to make sure the false negatives are as low as possible. Anthony, how much time I have?
You have.
Do we want to have Q&A, or do you want to
15 minutes.
continue? Do you want to have Q&A?
Hold on,
or?
let me just make sure I'm not telling you incorrect. Yes, we have room to 9:30.
Okay, so do you want me to continue, or do you want to have questions, or what
Do you guys like to continue, or would you like to stop for some questions?
I'm changing gears to health projects, so I'll be happy to just.
We'll see health? Let's go to
Yes,
health.
okay.
Let's go to health.
So, like the other project that was in mobility, our background is the data part. So we do have a lot of collaborators. We work with Erlanger Hospital, we work with Siskin Hospital in Chattanooga, we work with our occupational therapy, physical therapy, public health departments there. So we have two sets of projects. One is sensor fusion. We do a lot of remote medicine type of work that it's used for rehabilitation, it's used for sports medicine, for activity tracking, and then we also do some projects that, the same thing that we were talking about in terms of transportation, we're working on also in health to build a digital twin of that, and I will be talking about some of those projects. This is a project that was funded by NIH. The goal for this is, we know that this part of Tennessee is having a higher number of stroke patients. So that is where Erlanger Hospital came to us, and working with physical therapy, one of the goals was when a person has a stroke and when they go home, there's not much data about them after. So some come back for their therapy, some they don't. And even if they come, the number of physical therapists that they come back to is usually 2-3 times a week, if they come to all. So there's a lot of disconnection, and this is the work that we're currently, the app and everything is being developed. We're collecting some data. Like the transportation project, because this is a project that actually, it's not just a research, someone would be using it. There's a lot of work going on in terms of the colors, in terms of the font, in terms of all of those things, the size of the buttons and everything. And then so what this one is doing is it's assessing the risk of the fall. There are ways that and after a person had a stroke, usually one side of the body is impacted. So it's like how much the strength is coming back to that side on the arm and the leg. So there are different metrics that we are collecting over time. So the person, this is something that they can wear it and they can collect data over time. And then the doctors and the therapists are looking into it and seeing that the intervention needs to happen or not, or how useful, impactful was the medicine or the time of the therapy that they have given. Let me actually go to this one and I'll come back. Related to that, collecting data with sensors or with phones, another project that we are working on with the public health faculty, Gary Wilkerson, is we built this app called Flanker. What it does is it always has 5 arrows on there, and the middle, like they have to flip it to this direction of the middle arrow. Sometimes all the arrows are one direction, sometimes it's a mix. And the number of correct responses and how fast it has a correlation, and this is what Dr. Wilkerson has been working on with having concussion. This is a simple way of being used on the field versus there are other technologies, but that's what they are. Currently, this is being used in Colorado. There's a company there, Colorado Sport Evaluation. They're using it to evaluate for baseball athletes. We're using it at UTC. Other entities and schools in Chattanooga has reached out to us. They're going to be collecting data. This is basically understanding before getting on the field, they can do the test fast, and afterwards, if there was an injury and everything, to understand how did that impact based on the concussion. So this is another thing that we have been collecting the data over that. And then one other project that we are working on, again related to stroke, there are two parallel projects we're working on. One is, if a person with a stroke gets to the hospital, can we predict where this patient gonna go after their duration of their hospital, usually 2 weeks? Where are they gonna go? Are they gonna go to a nursing facility? Are they gonna go to Siskin, for example, a rehabilitation hospital? Can they go home? Do they need a healthcare provider at home or not? This is gonna be helping both the insurance companies, the doctors, the caregivers to have a plan. So we are working on we started with the data from Tennessee Department of Health first, and now we're working data from Medicare. So we purchased data from CMS, and we have been looking at it to see that predict where are they going to be discharged afterwards based on the characteristic of the patient, the type of stroke that they had, and the type of treatment that they have received. And again, all of these is about making sure that, like, can their intervention happen for a better recovery, for a faster recovery. And I'm just going to go through this quickly as well. Another project that we're working on is, we all know that the 30-day readmission is something that if you get readmitted within the 30 days, it would be the hospital's, the cost would go back to the hospital, no matter what was the cause of it. So that's one of the things that related to the previous project, that where the facility discharge is going to be. We're working on this project to understand, based on where they had been readmitted, based on the type of treatment they have received, what was the rate of readmission and what caused it, to be able to improve the previous model. So this is something that we're actually working on with Erlanger, and now we're expanding it. We just got the IRB approved. Again, those of you that work with healthcare data, you know how hard that is. But we finally got it approved with UTHSC, so we're going to be working with them on a larger data set for the bigger part, not just the Chattanooga data now. I mean, Erlanger, a lot of patients come to Erlanger from other part of Tennessee as well. But this is going to be allowing us, with working with UTHSC, to cover a larger part of the state as well, to understand what's going on. And again, our focus currently has been stroke. There are 3 steps of it. From the time the patient gets in there, can we predict where are they going to be, and what would be their chances of being readmitted? And when they are readmitted, if they go home, can we monitor them over a long period of time and understanding the impact of that type of treatment and such on their long-term recovery, not just how they were at the time of. I have 2 more slides. One is, this is the team behind all of this work. These are our great students at UTC. Again, it's not just UTC. There's a lot of students from other universities as well. And I love this specific picture first. When we started our connected vehicle project several years ago, and this was an NSF-funded project, that's how the whole thing started. We didn't have the test bed we have today. So we didn't have our cameras installed. We didn't have reference points. So 2 of us, Jose is tall, and I'm tall. So he and I would hold the cameras up, and then these 2 students with QR codes stand there because they were our reference points. So we have came a long ways in a few years, but this is just something that I think it's just amazing to look back and see that how this whole thing started. And I also have to say that the NSF project started because they wanted to see the cities that had gigabit internet, how can they take advantage of that? And our project was being able to communicate back with your vehicle in real time. So and the projects that we did was like looking through, being able to see the car in front of you, through the car in front of you and such. So this is what team has been working on. That's all I have. Thank you.
Nina, I have a question. More and more cars are coming with navigation systems, and we have our own, like Waze and Google and everything else. And you're collecting real data. Other cities are collecting real data. Folks like Mayor Williams that know their city real well may know this anecdotally and might start collecting data on it. But when something happens and all of a sudden hundreds of cars come off the interstate and start cutting down his streets, that he's going, oh no, not there, not there. Is there a way that cities can work with the manufacturers of these apps and softwares that, so when those accidents happen, you don't reroute them through areas that cause greater problems? Is there a way to take what they'll learn from data in the future, like you're collecting, and what they may know anecdotally, to try to avoid this?
So Waze actually, as one example, is they had made available their data to the cities and the state DOTs. For example, Chattanooga, we have access to the Waze data. And that's one of the things going on now, because a lot of times, road closures, for example, right? It's sometimes we know about it ahead of time, sometimes you don't, but then that's not part of the app yet. And so that, to your point, that's exactly the reason that they want to understand that local data be added to that as well to improve the routing algorithm. And one of the things we are looking, again, I didn't have any slide on our DOT project because it's not even a week that has been announced. So I have some graphs from the proposal, but that doesn't show much. But one of the things about that is, especially when we go with EVs, it had happened to us that at 1 a.m. we pulled into a charging station with 1% battery. And you know, when you have young kids, and this is 3 years ago, I had a 4-year-old and a 6-year-old in the car, you're freaking out because you're thinking of what's gonna happen. But it was because of that, exactly, because there was road closures and such that they routed us through a path that they didn't know about it. And so that is one of our goals, for example, for that project, to make sure that the routing and all, it considers more data than what is available, like anything in, you know, when we talk about optimization, adding any more variable, it does make it more complicated, it makes it slower and everything, but it's doable. It's not, I'm not saying we can include everything in there, but there are a lot of things that can be added to that routing algorithm. So those type of partnerships with industries are very important. Yes.
I think something that we would like to happen, and I think it will probably soon, is as we install our fiber and have control over it, have a war room to where we can kind of see what's going on with the cameras, we'd like to be connected to the interstate system so that whenever there is a backup, then it alerts us and I can adjust my lights accordingly to where I can flush the system without having a major issue right when school is letting out or when it's starting or when we have a concert that's going on or whatever. So that's something that being connected to the interstate system to where we can see this.
And you know, to your point, and so I think if there are data that can come from the interstate to add it, that would be great. But some of the things we're doing also, if the system would be able to, because again, this is adaptive system, so if it sees the traffic, if it knows ahead of time, it would be better, right? But even if that data doesn't exist yet, it should be adapting to that scenario because it is predicting and it's seeing the data coming from, like, you know, for example, in our case, coming from the highway. But you know, the events are great things to be added because you can predict for those things. And some of these, you know, you can't always look at Friday afternoons the same way because some of them have events, some of them didn't have events. So any of those additional data point that we can add into that, there was an event or not, that then the model can learn from that.